Good morning, and welcome to another episode of the Think Onward webinar series. Excited today to talk about the Geophysical Foundation Model. I'm your host, Clark Dever, and I just wanted to share. Please go to thinkonward.com and register. And while you're there, if you haven't been before, check out our challenges, bounties, and projects. It's a great way to earn some additional income with your skills that you already have. So today I am joined by Jesse Pizzell and Jeff Roth. Jesse is a data science leader with 2 decades of experience across multiple industries, government and academia. As director of data science challenges at ThinkOnward, he specializes in building AI systems and leveraging data science for actionable insights. His research spans cutting edge areas like generative AI, reinforcement learning for renewables, and vision transformers. With a PhD in geology from the Colorado School of Mines, Jesse's expertise includes geospatial data analysis, statistical modeling, and signal processing, making him a versatile problem solver in the tech and science space. And Jeff is a data scientist with over 20 years experience, specializing in geophysics, data analysis, and energy tech solutions. Currently at ThinkOnward's Innovation Labs, Jeffrey combines his expertise in geoscience and machine learning to address challenges in the energy sector. With a strong foundation in physics-based and statistical analysis, he has influenced capital project decision-making across his career, including 14 years at ExxonMobil. A problem solver and team leader, he excels at simplifying complex technical concepts for non-technical audiences. So excited to have both of them here today and excited to learn more about this exciting model. With that, I'll hand it over to Jesse.
Excellent. Thanks, Clark. Let me go ahead and I will share my screen here and then we can jump into things. Right on. Okay, so like Clark mentioned, today we are going to be talking about the Geophysical Foundation Model. We're going to be talking about our open source and open weights model. So kind of briefly give you a rundown of what we're going to be talking about. So we'll start with a introduction to transformers. So what are they? A very, very high level of how they work. Then we'll jump into seismic data, kind of talk a little bit about seismic data. What is it? How is it collected? Then we'll talk a little bit more about the application of transformers to seismic data. Then we jump into kind of the fun stuff, the Geophysical Foundation Model, or what we will probably be referring to as GFM through a lot of the presentation. Then we'll talk about applications of the GFM, Geophysical Foundation Model, and then we'll jump into kind of a short demo of how you can get started and rolling with this thing. And on the right-hand side of this slide, we have a screenshot of our Huggingface. So this model is on Huggingface for anybody to use. Once you get, you just got to hand over an email, and then you get full access to the model. So with that, I will hand it over to Jeff, and we can get started talking about transformers.
All right, thank you, Clark and Jesse. And I think maybe before we even start here, do we want to start with that survey question and sort of see where folks' familiarity with transformers is?
Sounds good. Yeah, we'll start this this poll right now. Let's see. All right, here we go. And I'll let you know as the answer's coming in, and then once it drops off, we'll share the results with everyone.
Great.
And I don't know about you, Jeff, but I think by far my favorite Transformer has got to be Megatron.
So it looks like we have weighted a little bit towards somewhat familiar and not familiar, almost a little bit of a normal distribution actually across the whole thing, but somewhat familiar definitely in the middle. And then Optimus Prime took it. So here's the results for folks, and then we'll get back into the game. If you have any questions, please use the Q&A section, and I will moderate for the team. They welcome your questions as we go along today, so we can stop and keep it more of a dialogue and dig in where we need to dig in. All right,
All right.
back to you, Jeff.
Perfect. Well, you can't go wrong with Optimus Prime. This is going to be a pretty brief overview. We're not going to make anyone an expert to transformers here, but we're hoping, hopefully by the end of this, we'll be able to move some of you folks that sort of are in the not familiar at all to at least the somewhat familiar with transformers category here. So what are transformers? They're a type of deep learning model that was first introduced in a paper titled Attention is All You Need way back in 2017. And the basic architecture you can see is illustrated here on the slide on the left. That's from that paper. The real key components that were introduced in that paper are the attention mechanism and the encoder decoder structure. So we'll go through each one of those kind of one by one. That self-attention mechanism is what allows the model to focus on relevant parts of the input and weigh the importance of those different parts. And so this was really solving a kind of a long-standing problem with machine learning models that enables it to deal with these long-range dependencies. So when you have a lot of text, you're putting in a lot of input into one of these models. Previously they sort of had to deal with these things sequentially, word by word by word, and you would run into some issues with when you had long-range dependencies across those inputs. And so this sort of allows it to weight the importance of different portions of the input and look at the whole input sort of simultaneously. And so that was a big way forward. The other key component is that encoder decoder architecture. And so if you look at that diagram, you can see there's sort of broadly two boxes there. Those are the encoder and the decoder. Now the encoder, the job of that is to convert the inputs, this original paper was natural language processing, so it would be text input into a numerical representation. Remember, these models work with numbers, not words, so they have to first be converted into a numerical representation. And so it's converting those into this feature tensor along with the context of the word surrounding it. And so that's where that multi-head attention piece comes to play. And for the encoder, it has what we call bidirectional attention, meaning it can pay attention to the whole input sequence. So, what happened before, what's going to happen at the end, the whole context. And so because it can do that, it excels at extracting meaningful information from the input. So think of things like natural language understanding, sequence classification, and question answering, things that require really deep understanding of the input. The second piece is the decoder. And the decoder is a lot like the encoder in that it also is converting your inputs into a numerical representation. However, in contrast, the encoder, it has only what we call a unidirectional attention. It can only look backwards. It can't look into the future. And so basically, if you think about that working, it's like it's predicting the next likely word. So predict the next word, predict the next word, predict the next word. And it can look back at what it's already said and use that to sort of predict the next word, but it can't really look forward. And so these types of models excel at causal language modeling. So think natural language generation, guessing the next word in a sequence. Now, when you combine these two, the encoder and the decoder, this is what we typically refer to as a sequence to sequence model. That's where, the real magic can happen because you can have the decoder taking the output of the encoder as input and then have it create a sequence of words in what we would call an auto-regressive manner. And so as it's predicting, the next word, it's looking back at what it's already created, and so in a regressive manner, it's continuing to build that output. And in these models, the job of the encoder is to understand the input sequence, and the job of the decoder is to generate an output sequence based on that understanding that's provided by the encoder. And so these types of models excel in tasks that require understanding and text generation. So think of things like summarization, translation, or question answering.
Very cool. So I guess to make sure I'm on board with this and understanding this. So effectively what these things are doing is we're taking like something like text and we're turning it into a really long vector of numbers, feeding it through this thing, and then our decoder is basically taking our long number and turning it back into text in a certain direction. Is that right, Jeff?
It is. And the way I kind of like to think about these encoder decoders, if you find the idea confusing, the old adage, think before you speak. The decoder, it's just a word prediction machine, right? Predict the next word, predict the next word. That's kind of like the sequential speaking part. But when you are thinking about what you want to say, you don't think necessarily in a linear manner, right? You're making connections, you're kind of thinking in this nonlinear fashion. You're understanding the whole concept. That's really the encoder's job, right? And so, I'm sure we all know people who maybe speak before or speak without thinking. They're all decoder and no encoder, all right? So you gotta for these types of models, think of the encoder as the thought process and the decoder as then formulating what you want to say.
Yeah. Perfect. Excellent. So sounds like I've been paying attention. I've picked up something here so far. We're ready to kind of talk a little bit about the history of transformers.
Let's do it.
All right. So let's talk a little bit about the history of transformers. I think this is kind of a cool space. On the left-hand side of the slide, I really like the comparison, how we have kind of the vision bar on top in blue. Um, and I really like these timelines because we've got vision broken out. We've got this kind of cross modal in the middle. And then we have language modeling in yellow at the bottom there. And, you know, long short-term memory and recurrent neural networks, those were kind of like, that was the go-to up until about 2017 when transformers were first really applied to natural language processing. That's really where they came from. So 2017, that paper came out. Um, things like Jeff was mentioning, it's a sequence to sequence. You're converting from one sequence to another. So you're looking at things like translation, summarization, text generation, and really, BERT was kind of the first that like the OG transformer that came out. The other one that I think everybody's probably heard of in some way, shape, or form at this point is GPT, or Generative Pre-trained Transformer. Um, that's ultimately that generative side of things. So that was where things really started with transformers, was natural language processing. Then in about 2020, vision transformers really started coming out. So think of that as we took transformers and adapted them to image patches, treating them as a sequence of tokens. So think of it as like taking an image and breaking it down into like almost a sentence to an extent. Um, so similar idea as words, we're treating things as kind of like sentences, but we're doing it to images. What's really cool about them is they're really competitive with convolutional neural networks, kind of the like, traditional. I was reading the other day, it was like convolutional neural networks, I think, were proposed in like the 80s, 90s, something like that. Um, so it's kind of cool to see transformers, pick up and be just as competitive with these methods that have been around for a really long time. Then I think the last thing I want to throw in here is talk a little bit about masked autoencoders. Um, so the idea behind masked autoencoders is ultimately you're masking out some portion of your data set, and then your model's learning, how to reconstruct the missing parts of the data set. So think of it like what's a good example? Like Mad Libs, where you're like, okay, here's a word, fill it in, and make this a full complete sentence. So a similar idea where you're getting rid of chunks of words and filling them in. So we'll talk a little bit more about masked autoencoders here in a bit, but next we'll jump into talking a little bit more about masking.
So,
So Jeff
Jesse,
would, yeah,
before you move to next, I'm just kind of looking at this chart and I'm seeing, On the NLP side, you've got all these things, LSTMs, different types of attention, and then you suddenly you see transformers, and all those things have gone away. And it's sort of similar with the vision side. You've got these recurrent neural networks, convolutional neural networks, and then it's sort of like somebody put a stake in the ground with vision transformers, and it's just as far as you can see. Would you say, I mean, have these sort of made these other models obsolete, or is this sort of where things are going, do you think, for the future is more transformer based?
Yeah, that's a great question. I think most things are headed transformer based. Attention is really, really impressive with what it can do in these models. That being said, I've seen examples of convolutional neural networks and transformers, and they're pretty, you know, having pretty comparable results in similar tasks. But the cool thing about transformers is these self-attention maps are just amazing what they can do, and how they're learning context along the way.
Very cool.
Yeah. Well, with that, let's talk a little bit more about these attention these attention mechanisms and masking.
Yeah, so that would be helpful to maybe walk you through an example of what one of these transformers, how it kind of works in practice. Again, this is a sort of a language example, and this could be either an encoder or a decoder. Probably in this particular example, since we're doing masked word prediction, typically an encoder would be used for this type of a problem, because in order to predict what word is being masked, you really have to know, you have to have an understanding of the input, right? In order to understand what the right word would be that's being masked. So likely an encoder, but so we'll start at the beginning. We've got an input sequence. Transformers are awesome. And of course, again, machine learning models don't understand words, so we have to convert that to some type of a numerical representation. And so we perform what's called tokenizing. We're going to tokenize this input sequence into words, or probably even subwords or root chunks of words. And so here we have broken it down into those tokens transformers are, and then we've masked one of those tokens. And so we're going to vectorize that into a numerical representation. And then you see below that, we add a positional embedding. And that's really important, because in order for our encoder to understand the context, it has to understand where in that sequence those words are located. It has to understand how they exist in context to the words around them. And so we add that positional embedding into those vectors. And then we move into the encoder or decoder proper. You can see that first piece there, that multi-headed or multi-head self-attention. And that's kind of, just like the flux capacitor is what makes time travel possible. It's that multi-head self-attention that really makes the what the encoder does work, right? That's what allows it to, and sort of, and it's apt in this case, right? Because that in an encoder, not only are you paying attention to what's happened in the past, but you can actually look into the future and understand the whole input sequence at once. And then that's fed through some various, normalization and feed forward networks to understand the features, and then finally outputs. Again, it's going to be a numeric representation that will go through some type of activation function, softmax or something, in order to predict what the most likely word is for that masked feature. And so that's sort of the basic flow. Obviously, there's a lot of variation on that, depending on whether you're working with an encoder or decoder or a sequence to sequence model. But that's sort of the essential idea for how these transformers work.
So it sounds like at kind of a really high level, we are playing Mad Libs with these machines. We're just saying, okay, let's get rid of some words and have you fill in the blank to an extent. Is that right?
That's pretty much it. Yep, you got it.
Right on. I'm learning things. All right, let's talk a little bit about vision transformers. So I guess a good example, if we're in the language space, if we're playing Mad Libs with the machines there, would you say that vision transformers are kind of like playing like Pictionary to an extent?
Yeah, I feel like there was a game I used to play as a kid like this, where you had all the different, tiles, and you kind of have to figure out where they belong in the image. It's
Yeah,
kind of similar.
yeah, it's a good way to look at it. It's like yeah, it's kind of like a puzzle to an extent, but also not really. I don't know. It's kind of something totally different. So let's talk a little bit about vision transformers. So, kind of the cool thing about vision transformers is we're doing the same thing. So we're masking out images rather than words. So in our natural language example, we're just getting rid of words. In our image, we're actually just masking chunks of the image and kind of doing the same thing. So what is really cool is like in the this image on the left here. So we have this medical imaging example, and up here at the top, you can see we have this kind of image of a human body, and we've chunked it into these 9 patches here. And ultimately, kind of this example down below is we're masking out chunks of this thing and saying, okay, fill in the blank, draw the part that is missing. And so we're using transformers to do that. So this is where that masking comes back in. So some of the benefits, the multi-head attention lets the model look at multiple patches. What I think of is like looking at multiple patches at once, kind of giving it that better understanding of all the different patch features. Um, what I really think is cool is this is like self-supervised pre-training. So instead of having labels and needing all these certain things, we're just kind of getting rid of chunks of the image and saying, do your best, fill it in, and we know what the ground truth looks like, so we can compare how the model does. So the supervised learning is really beneficial for training these encoders. So that's kind of the left hand side of this diagram is we're teaching the model how to encode our different patches, and then ultimately we're looking for this decoder up here in the upper right hand side. This is where all the cool stuff happens. This is where we can build out things like segmentation heads, or different downstream tasks. You might hear that term an awful lot. Is these downstream tasks? These are like segmentation. These are interpolation that we'll talk about a little later on. Denoising, pretty much anything that you can dream up, you could probably do it for a downstream task. Does that make sense, Jeff?
Yeah, and I think what's really cool about this is this idea of sort of transfer learning, coupled with Jesse mentioned this masked auto encoding, and so that masked auto encoding in that first step, that allows us to train on a lot of data without needing labels, which is really advantageous. And it's kind of where you're teaching this thing how to understand what it is that we're interested in. So for language, you're feeding it a bunch of text, and now it understands our language. In this example, you're feeding it a bunch of these images, and now it kind of understands what the human body looks like in these images. And then you can transfer that learning to that downstream task. And that's where you come in with a small subset of labels and say, okay, now I want you to be able to show me like what in this image looks like it could be a precancerous cell, or show me these various organs, or whatever these sort of downstream tasks that you can think of. It requires a much smaller labeled, high quality labeled data set to give it those downstream tasks. It's very
Yeah.
cool.
So it sounds like it's like if you had an intern that came in that's seen a lot of different stuff, and you're like, okay, you've got 8 weeks here, focus on this very specific thing. They could do a really good job at that, having seen a wide variety of stuff in the past. Does that sound about right?
Yes, that's exactly it. Yeah.
Right on. Excellent. Well, let's keep moving on. So we talked about transformers. Now let's talk about seismic data. I guess, that's kind of the next big step is what is seismic data? I know, Jeff, you are one of our resident experts in geophysics and seismic data. So teach me about seismic data, what it is, what are we even talking about here?
Sure. So yeah, let's get specific to our application here. And I don't know what everyone's background is on seismic, so we're going to do a very gentle primer here. And I will say, disclaimer, this is going to be pretty broad brush strokes. So I know we probably have some geophysicists in the room. Don't beat me up too hard on this because we might be not entirely precise with the way we're talking about this, but we just want to make sure everyone has sort of a baseline conceptual understanding of what seismic data is and how it's a little different from maybe working with other types of image data from a machine learning perspective. And so probably the best way to understand this is to kind of take a few minutes to walk through how seismic data is actually collected and processed. On the left there, I've got a real schematic view of kind of a cross section of the Earth, if you will. Those colors are going to represent different layers in the Earth that have different acoustic properties. All right. And so the density of those layers and or the velocity at which sound propagates through those layers give them different acoustic properties. And when sound energy encounters those changes in properties, energy is going to get reflected, right? And that's what we record. And so we've got a little animation to kind of show how that works if you want to kick that off. So there you see a source, and on land this could be a vibrational source from a vibration truck. It could be dynamite in the more in the olden days, still used sometimes. Or if this is ocean data, it would be some type of an air gun. So they set off a pulse, an air bubble in the water column, and that of course creates a sound pressure wave. It propagates as a wave, but we're going to represent it here as ray paths just for simplicity. It's a little easier to draw. And so you see these ray paths, and they're reflecting off of these various layers, and they're being recorded at a sensor. And so that's represented with that triangle there. And you can almost think of this as, as almost like an audio recording. It's recorded as a time series at that sensor. And so it's hearing these echoes, right, of these reflections coming off of these layers. But if you think about it, one geophone, one sensor isolated on the Earth's surface, it has no idea where that energy came from, right? All it hears are these echoes. It doesn't really know that it came from these reflection points, way off over there. And so if you animate the next piece, is to kind of give a sense of that. If you were to hang that audio recording right at the sensor location, you hear all these echoes represented by these wiggles, but they don't actually line up with where those reflections occurred in the Earth's surface. And so that's where sort of the dark art of seismic processing comes in. Well beyond the scope of this talk, but it includes things like binning, stacking, velocity modeling, and ultimately migrating, or take that energy and we migrate it back to where those reflections occurred in the Earth, or at least where we think those reflections occurred in the Earth, in order to create an image. And so if you select one more, you'll get kind of an idea of what a seismic image might look like. And so some key points about this, when you take an image with a digital camera, that image is being projected onto a sensor. That's a sensor that's full of pixels. And so you have sort of a pixel-based image. Seismic data is a little bit different in that even after we've processed this image, everywhere from acquisition to process, it's trace-based, right? We have a trace for each location on the Earth. And to sort of drive that point even further, on the right, we have an example of sort of a 3D processed seismic cube. And you can see all those they kind of merge together, but there are all these little points on the surface of that cube. Each one of those dots represents a trace location, right? And so there's a 1D trace at each one of those points, and it's those collection of traces that makes up the image. And you can sort of see we've got a little schematic of a acquisition boat. This is how this data is acquired in the ocean. All these long streamers behind and sources going off, and so you're collecting, thousands, tens of thousands of these traces that make up the image.
Yeah, that makes sense. So it's like I'm trying to think of kind of a good example is you during I know in Seattle it's a big deal when the Seahawks play and people jump up and down and all the seismic stations around the city kind of like collect the seismic waves of during the game. Similar idea, I think. These different receivers are picking up the different waves, and ultimately, geophysics is you're taking these kind of long strings, these time strings, and stacking them all together in different locations. Is that am I following?
Yeah, and there's again pretty far outside the scope of this talk, but all kinds of different methodologies that go into seismic processing, and particularly in that migration piece. And if you go to a geophysics conference today, there's always new methods coming out for how to more accurately migrate that data. Um, but yeah, that's the general idea.
Right on. And so like these, each one of these traces is like its own little individual kind of piece of information, right?
Yes, that's right. And sort of again to sort of drive home that point, these images are not, they look like an image. And so, probably the first thought is, well, can't we just treat these as an image in a machine learning model, kind of like we did and it showed in the last slide. And you can. Certainly that is one way to approach it. But I think we think is that it's an important distinction that these images are not so much pixel based as they are trace based, that is sort of the fundamental unit or concept in seismic data is the trace and not really a pixel.
Okay, that makes sense. So now that we understand a little bit about transformers, kind of that high level, a little bit about seismic that it's collected and it's kind of these time series that go through this black magic process. Um, I guess, let's talk about applying transformers to seismic data. So as much as I love in my mind to think that it is like Optimus Prime sitting there interpreting seismic through different software by hand, like clicking his way through, picking horizons, that sort of stuff. You know, why did we think that this would really be a benefit to seismic data? This the scalability and efficiency, having transformers that can look at these large data sets, they can train on these large data sets really efficiently, you know, makes them perfect for seismic data. Seismic data is pretty good size, makes it perfect for transformers. Next, these long range dependencies. That self attention mechanism is great for picking up long range dependencies and these really complex patterns in data sets. That makes a really good seismic interpreter. If they can see everything kind of like, what I think is see all at once, it makes them pretty good at picking things out or filling in the blank or, all of these other kind of downstream tasks. And then lastly, versatility. Those downstream tasks are so important. Being able to take a model and really adapt it, go from like robot mode where you're walking around to like a semi truck or a car or a helicopter or something, change and adapt for these downstream tasks in seismic data like interpolation, denoising, segmentation. That's huge to be able to quickly adapt to new situations.
So I think we might have another survey question that might be appropriate here.
Yeah.
So yeah, Jesse just mentioned, the versatility of being able to use these for these types of downstream tasks. So we're just curious, what application of transformers do you think gets you most excited? Is it interpolation, denoising, some type of segmentation or interpretation, property prediction, or if you have some other ideas, you can post them there in the chat.
So we're seeing a lot of segmentation, interpretation, and then property prediction seems to be a pretty strong second at this point.
Nice.
So we've had about
Nice.
60% participation. I'll run a couple more seconds for the latecomers, but then I'll share the poll results.
Yeah, I'm all about using them for segmentation interpretation. That is like, that's saving years of people's lives clicking and picking.
Absolutely.
So here we go for the
Let's see,
group.
where do we end up? Interpolation, denoising, segmentation, property prediction, and other. Other, I'm kind of curious, if anybody's got, if you want to tell us what you're interested in, I'm always curious to see what ends up in that other bin there at
Yeah,
the end.
you might have to use the Q&A feature to drop them in. Unfortunately, I don't know if I have chat enabled for the group, so
Okay.
apologize for that. But all right, back to you, Jeff.
Right on.
All right. So let's talk a little bit more about ThinkOnward's Geophysical Foundation Model, where this idea came from. So the model was really born out of one of our challenges. It's called Patch the Planet. And the challenge posed was given 550 real and synthetic seismic volumes, can the challengers complete or fill in missing blocks of data within those seismic volumes? And as that challenge was ongoing, the challenges team here at ThinkOnward will frequently research possible solutions to challenges that are in development or live. And it was during that research process that the team developed a new transformer-based foundation model utilizing trace masking. And so, Jesse, would you like to maybe elaborate a little bit more on what this idea is?
Yeah, yeah. So we've talked a lot about our masking and playing Mad Libs and Pictionary and all of these fun games as good analogies. And then we talked a little bit about seismic data, and we really brought up the idea that the trace is kind of analogous to like our sentence or our words that we're masking. So the team really started researching, what's been done in this space, and really, kind of the original method that came out, I think it was last year, was using these patches that we see kind of in most mass autoencoders, where we're just patching, taking these 14 by 14 patches. Clark, looks like you got a question.
Yeah, so Hector asks, is it possible to access the original challenge?
Um, Ooh, good question. So we have all the data. The data is actually publicly available all on Huggingface for you to download and use as you so desire. Um, the If you're registered on the platform, I think you can see the challenge outline. Um, and I think there's also some more information over on the Think Onward forums for the challenge as well.
We had a follow-up question from Belkacem. In which step do you think in processing seismic data we can use this concept?
Oh man, oh gosh, I really like the denoising idea. Like, I think that's such a cool application of it. Jeff, what about you? What do you think?
Yeah, I think there's so many possibilities, to be honest. I think we're just starting to scratch the surface on that one. The sort of I think where we have looked so far, sort of the lowest hanging fruit would be, post migration, post stack, sort of looking at your final image and doing some kind of a cleanup, like Jesse mentioned, like a denoise. Like that seems very obvious because it's something you could train a model on with, a small set of labeled data, noised and denoised, and then apply that on a kind of a final image. But I think there's a lot more that we can do there, even potentially going back into sort of pre-stack data. So stay tuned.
The,
we'll be
the
we'll be
other
doing that going forward for sure.
the follow-on comment was, how about static corrections?
That would also seem like a pretty straightforward application, I would think. Yeah. Yeah, I mean it's hard to imagine there are, places where you couldn't apply these in some form all along the processing chain.
Yeah. Excellent. Yeah, so I'll keep going, talking a little bit about the ThinkOnward geophysical model. So, as we mentioned, our traditional methods here, we're using these patches. What we basically laid out and trained in our model is, instead of patching out these 14 by 14 chunks and saying, all right, fill in the blank, we thought, okay, our seismic traces, these vertical traces, these are our key components. So let's mask out traces. So rather than a square patch, let's do kind of these long um, rectangles and mask out chunks of traces. Um, so we ultimately said, okay, let's take the patch the planet data, let's train on that, and let's just mask out traces and see how it does. And on the bottom here, you can see, this is the original seismic data. If we get rid of 75% of it, so it's only what you can see here is what the model can see. And here's the reconstructed seismic line. So it's doing a pretty good job filling in the blanks here. I mean, that's better than I would do it at a game of Pictionary, of like, okay, let's fill in what's going on in here. So I think it's doing a pretty good job here. Let's see. Anything else that I want to say on this slide? Ultimately, at the end of the day, masking out these traces really honors kind of that key component of seismic, the trace. Um, any other thoughts you want to add here, Jeff?
No, I think you kind of hit on the main concept, right? We really um, our approach to this problem was that, again, seismic data is collected in traces. Traces kind of represent that fundamental token, if you will, of seismic data, not so much the patches or pixels, right? And so by masking traces in that pre-training step, we feel that more honors sort of that fundamental aspect of seismic data. And in our benchmarking of that, have found that it is, using like structural similarity indexes and, to benchmark those results, have found that to be more performant than a patch-based approach as well.
Yeah. Clark, another question.
Yeah, Maggie asks, how about deghosting and demultiplying? I don't know how to conjugate that.
Mm, multiple, yeah. That's actually a excellent question, and I would say that yes, that's something that we are kind of thinking about internally, is demultiple. I mean, it kind of follows a sort of similar approach as, like a denoising would.
Yeah.
Deghosting is an interesting one that I hadn't really thought of, but I think that would be worth investigating as well. I mean, in a more traditional approach, you're dealing with deconvolving source and reconvolving with a, target wavelet or various, attacking bandwidth and that kind of thing. But I wonder if this approach would be a sort of a more performant or faster way to get at that solution. So that's something that's worth thinking about.
Yeah. I strongly recommend. I'm going to always promote challenges. That's my favorite part of the day. Um, Definitely check out the Image Impeccable challenge. There's some cool examples of seismic multiples, and it was a challenge that just closed that was looking at denoising and removing multiples from seismic data. So definitely check that one out. Excellent. Let's see. So let's talk a little bit more about the GFM. So some cool applications. Everybody had some great votes, some cool comments on what you're all thinking. Here's some great applications of the Geophysical Foundation Model. Interpolation, that was what it was built for. It's really good at that. Denoising, that's a really cool downstream task that's pretty easy to get at. Segmentation, anything, if you can dream it, you could probably build it, as long as you got the data. I think that's kind of the big thing, is if you have the data to do what you want to do, you can fine tune it very, very quickly. I don't know. Anything else you want to throw out there on this slide, Jeff?
No, I don't think so. That pretty much hits it. These are sort of what I would call some of the lowest hanging fruit, I think, for these kind of things. And like I said, we're just sort of scratching the surface here. And so, the world's kind of your oyster in terms of downstream tasks. If you, like you say, if you can dream it, let's try and train it and see how it does.
Yeah. Clark, another question.
A good team member, Bao, asks, does GFM honor amplitude preserved processing and imaging? And he says hello.
Ooh. Good, always a good question here from Val.
Yeah, I think it does, and ultimately it would boil down to how you would normalize the data set before fine tuning for different tasks. If you're renormalizing your amplitude out, and ultimately that was kind of a big question for the denoising that we came up against, is like, how do we deal with the amplitudes? Are we preserving them? Are we squashing them down? Are they being stretched out? Are we, is there something funky going on with the amplitudes when it runs through the GFM? But so far, we have no evidence that it's doing anything weird with amplitudes.
Yeah, I think that's probably ultimately going to be one of the bigger challenges for these types of methods is, do you have faith in sort of your amplitude and phase preservations? Typically a processing stream is very deterministic, and we, I think as geophysicists find comfort in that, because we want to every step of the way say, are these amplitudes, have we preserved the quote unquote right amplitude? Can I map this back to an actual reflection coefficient number or something like that? Some of these, it's going to be remain to be seen how well I think these models do that, and that kind of trust is only going to come through a lot of QC and testing, right, to see just how well they're doing in terms of preserving um, those amplitudes and phases. It's a really
Yeah.
good question, Bao.
Well, I think our next stop is like the fun part. Yeah, the part that everybody came for. All right, I'm going to stop sharing really quick. And I'm going to switch and make sure that everyone can actually see this. We're in presentation mode. And we will share a tab here. All righty. So let's run through kind of a quick demo. For reference, this notebook will be on our GitHub repository for the Geophysical Foundation model. So if you're like, wow, you guys ran through that in 10 minutes, holy crap, don't worry, you can find it, you can get access to it, you can get access to the model, you can get access to the data. It's all open source, it's all out there for you to work through as you so desire. So ultimately, what we're going to do in this notebook is download some data. So we're going to download some of that Patch the Planet data that we talked about. We'll just download a single volume. For today's demo, we're not going to download anything because as much fun as it is watching a progress bar, I've already pre-downloaded everything. But in this notebook, it installs everything you'll need. So Huggingface integrations, PyTorch, all the things you need to get up and running. And ultimately, it goes through, downloads everything, sets it up, and then runs through the whole pipeline for interpolation. Because again, that's what this was originally trained to do. So if we start off here, and I think I already ran through this once this morning. So just do some basic imports, and then to kind of the key thing here is to download the data and the model. You need a Huggingface account, and you need access to the model. Again, just an email, boom, you got access to the model, good to go. And I think Clark just shared our Huggingface in the chat here. So once you have access to the model, I even gave you a link to how to set up an access token. So this way you can just create an access token. So you can use the Huggingface Hub package. This is really handy to download data, download models, kind of anything you want to do. You can do it from within Python. So it's really handy. I'm not going to run this, but it basically logs you in using your access token, and then you can pull, push, treat it just like you would for Git. This next cell here, we have our data repository. So again, this is the Patch the Planet data set. And then I have a specific seismic volume that I'm after, and it comes down in a Parquet file here. And then we have our Geophysical Foundation Model repository here as well. So ultimately, this cell just grabs everything we want. So our data set and our model, and downloads that to my local device here. The next step, really, we're just converting our Parquet file to a NumPy file. And then this next function here is just masking. So in this case, we're getting rid of some of our seismic data. So here I've just, because for ease of use, I've just hard coded. We're just going to mask trace number 40 to trace number 110 in our seismic volume. You can change this. You could build a, like I'm just daydreaming, you could build a Huggingface space that does this automatically, and you can adjust sliders and get rid of chunks of seismic, or whatever you want to do. The world is your oyster. So we'll run that. This next cell down here is I like visuals. I'm a very visual learner. So here we've got our seismic on the left-hand side. So this is just our synthetic seismic volume from the Patch the Planet data set. And you can see this is our chunk of seismic. We have nothing in this area here. So this is what the model will see. And then Jeff, remind me what a mask is again here.
Right. So the mask is basically just showing us, right, where that data is, where there's data and where we've removed it essentially from the cube. So you take that mask, which is just ones and zeros, multiply that by your seismic, and you get sort of that image on the left there where we've cut some data out.
Got another
Just to
question.
confirm, guys, this is on GitHub, right? So I should post the GitHub link for this notebook.
Yeah.
Okay, awesome.
Yeah. So that.
Yeah, Anna asked, so I will put that in chat right now.
Yes. Yeah. Perfect. All right. So we've got our masked seismic here. So we've got our mask, we've got our seismic. Looks cool. All right. So now comes the fun part. So we're going to create an instance of our model. So this is our model here. This is also on GitHub. So once you download this or fork it, clone it from GitHub, that's really that's the big hurdle there, is pulling it down from GitHub. And then ultimately, to load up our model weights, super easy. We're just going to grab these pre-trained weights that I've already downloaded and load them into our model. And I think the weights are like 1.5-ish gigs in size. So not huge, but not tiny. And so here we can see that we've loaded our model weights, and then said, if we've got a CUDA enabled device, throw it onto CUDA. Otherwise, we'll just run it on CPU. On this device, I think I'm just running on CPU. So we've got everything loaded up here. You can see a little bit of information on our model here. So we're good to go there. Looks like everything loaded up nicely. And then the fun part, or like the magic part, which is the interpolation part. And so for interpolation, like a vast majority of this is just kind of resizing things. So we want to resize the seismic slice and the mask to the shape for the model to ingest. Then we're going to get the number of visible patches, run inference. This is like the run inference part just kind of still blows my mind, that it's literally just this line right here, like just a single line, and that's it. The rest of this whole cell is organizing. Now, Jeff, why is it so important that we do so much data prep and data cleaning for making predictions?
Well, of course, the model, it expects the data to come in a way that it was trained, right? And so most of this, it looks like a lot here, but it's mostly just making sure that, we've got things in the right size, that we don't need to, like, for instance, transpose our array and our data doesn't come in sideways or backwards or upside down and that kind of thing. And so it's just getting it into the order that it expects to see from its training.
Yeah. And then this last bit down here too is like really just combining our model with our predictions, or sorry, our model with our predictions, our predicted values with our actual values. So here, if I run this cell, it's going to go through, run our predictions, and then it'll spit out a nice happy image. There we go. And so you can see that area where we had that was masked. You can see it's done a pretty good job filling in what was missing. So it does, if I look at it really hard, I can see it as it gets deeper, kind of getting a little fainter, but overall does a pretty good job. It's a pretty good, I would want to have this on my team for sure, playing Pictionary with Seismic. So that's kind of the high level GFM in a nutshell. Everything that you need is on GitHub and Huggingface. So I will jump over to those tabs really quick. So here's our Huggingface page. Here's our Geophysical Foundation Model. A little bit of information on where it came from, who developed it. It's under Apache 2.0 license. Got some more information on a poster presentation that we did this summer that Mike McIntyre put on for us at AAPG. Some cool downstream use ideas that we've got in here. My favorite, the out-of-scope use. It was trained on seismic data, might not do well on other data. I don't think it would do well on images of kittens and dogs. But I think a cool application like ground penetrating radar, GPR, would be so cool for this to apply. Let's see what else. Some example usage, training details, evaluation, metrics, kind of everything in here that you need to get started. Question, Clark.
The GitHub link doesn't have the notebook, so the audience is asking if the notebook will be made available. Can we?
It will be there in like 5 minutes after the webinar closes.
Just need to do a little push. We'll be good to go.
Yeah. Right on. Excellent. And then I'll jump over to GitHub here. So here's our Geophysical Foundation Model on GitHub. So basically just a carbon copy of our model card here on GitHub. And then this Elastic Vitme Python file, this is our file that has got everything that you need to get started in it. So it's got our patch embeddings, it's got heads, custom heads, and then this is our trace masking here, this Elastic Vitme. So that is all on GitHub, and the notebook will be merged in like 5 minutes after the webinar, not even that, is over. And then the last thing that I wanted to show everybody is, if you have not been to our forums, we now have a Geophysical Foundation Model forum on the platform. Definitely check it out. Come hang out, ask us questions, have a conversation with us there. That's a great place to get in contact with us. GitHub's a great place, Huggingface. But this one we'd monitor, and we'd typically get back to people in about 48 business hours or less on this forum.
So Jesse, I have a question.
Yes.
We've released this thing on Huggingface. It's up there on GitHub. If I'm really jazzed about this and I want to get started on this today, do we have any like challenges upcoming where one might be able to apply this kind of flow, or what's the best way for me to get started on this thing and really get my hands dirty?
Yeah, again, I'm biased to challenges. I love challenges. We have the dark side of the volume challenge right now, which is think of it as like segmenting out subsurface faults. So find and map the faults in the subsurface. This would be a cool downstream task. You've got a whole, I think we've got like 500 gigs of seismic volumes that have labels with faults in them up for that challenge. That'd be a great place to start. If you want to like work on other seismic data, check out the Patch the Planet data set on Huggingface. We've got a bunch of other data sets and models that are coming to Huggingface soon, but I would say like start with building out a classification head for segmenting faults and hop in the dark side challenge. 10 out of 10 would recommend.
Super cool, super cool.
Yeah.
All right, so we've got, we're at time or overtime, so the two questions in the chat. Earlier you had some interpolation. How can you make sure that data is correct? The interpolation is correct.
Yeah. So if you've got a ground truth data set, structural similarity or mean squared error, great options to make sure that that it matches. If you don't have ground truth, then it would be kind of a human in the loop alignment type problem that you would have to go through in QC to make sure that it makes sense.
Yeah, that's
Right.
for sure. Yeah, and to be sure, in some of these examples, like Patch the Planet, we're patching out very large portions of the data. In a more realistic, real world environment, maybe you only, have a couple of drop traces or something or smaller pieces. It's unlikely to be missing 25% of your data that you're trying to interpolate. But yeah, that's absolutely right. It would be interesting to put in there some type of uncertainty estimate. I think that would be cool to think about how one could come up with an uncertainty map for those predictions too. But yeah, I'll leave that to people to try out.
All right, so the last question I have in Q&A, and you're getting lots of applause from the audience in Q&A right now, but do we intend to release, or is there already an example of denoising and segmentation?
Ooh, they're coming. So we've got some. So if you look at the Image Impeccable challenge, the baseline score on that was denoising from the GFM. So check that out on the Image Impeccable challenge. That one is coming soon. We've got a whole slew of kind of downstream tasks that we're looking at that are in the works for release.
Yeah, Maggie says horizon picking might be another thing that GFM does a good job of. So I think we agree that might be an interesting one. Um, cool. Well, with that said, I want to be respectful of everyone's time. I want to thank Jeff and Jesse for sharing their expertise in this model. I know everyone's excited to get using it. Great work to the team. If you're still here in the webinar, please take a few moments to fill out the 5-question survey after this. It helps us get better. It helps us know what you want to learn about and what we can present in the future. And if you're not registered on ThinkOnward.com, you definitely should, so that you stay up to date on future webinars about this geofoundational model, because we're going to keep releasing new things and showing new ways to utilize it. So we're excited to be on this mission. All right. Well, thank you, everyone. Have a nice
Right
day.
on. Thank you all.